Hello everyone, I am Madhur Model from Professor Dr. Madhav Nipene's research group at University of Central Florida. First of all, I would like to thanks to ANPA for providing the platform to present one of my research projects. Here in this talk, I would like to present where I studied the electronic structure of a layered ultramagnetic compound CONB4S8. The technique we used is called angle resolved photoemission spectroscopy, which is a modern version of Einstein photoelectric effect. So here in this slide, I would like to explain how the angle resolved photoemission spectroscopy, or shortly RPS, works and how we study the electronic structure of the quantum materials. So this is a sample. So when we shine a sample with sufficient energy of photon, then electrons are ejected from the surface of the sample with a certain angle. So those photoelectrons are actually captured by the hemispherical electron analyzer. So then we use the energy and momentum conservation and study the energy versus momentum or the electronic structure for a particular high symmetry direction, as well as we can study the Fermi surface or momentum along y-axis and momentum along kx-axis. The Fermi surface and electronic structure actually carry the properties of the materials. So here the kinetic energy of the photoelectron actually depends on the incident photon energy, work function, and the binding energy. So when we would like to dislodge an electron from the surface of the sample, then we just need to work for the work function that actually required energy or work done by the incident photon that actually dislodge an electron from the surface. So if we want to dislodge an electron from the bulk of the sample, then it has to overcome the binding energy, and for that we should increase the incident photon energy. So, as this material is a newly discovered magnetic phase called ultramagnet, so in this slide I would like to explain the basic differences of these three magnetic phases: ferromagnet, antiferromagnet, and ultramagnet. So to explain these three magnetic phases, I bring this schematic from Lever's Maxwell papers, where we can see nicely in this schematic that the ferromagnet has, of course, net magnetization, and due to the break of time reversal symmetry, we can see the spin splitting bands as well as the isothermic Fermi surface. So in the antiferromagnet, the opposite spin sublattices, they are connected by translation or inversion transformation symmetry. So due to that, it has spin polarized or spin degenerate band, and as well as spin degenerate Fermi surface. So on the other hand, in ultramagnet, these two opposite sublattices, they are connected by rotation transformation symmetry, and the net magnetization is 0. But due to this rotation transformation symmetry, it breaks time reversal symmetry. For that, we can observe the spin polarized band in the high symmetry points, as well as in the Fermi surface we can see the anisotropic electronic structure for G or I wave natures. So up to now, there are a handful of materials actually show these ultramagnetic properties. So among them, MNT or manganese telluride is one of them, where they observe the spin polarized band along M gamma M high symmetry direction, and these materials has spin polarization around like 370 MeV at k is equal to 0.35 angstrom per angstrom, and these materials also showed the G wave nature of ultramagnetism. So another material is CrSb, chromium antimonide, which has larger spin polarization, which is around 600 MeV, and these materials also shown the G wave nature of ultramagnetism. So another material is CO140SOT. This material actually studied by my colleague Milo Sprague, where he observed the ultramagnetic spin splitting phenomenon along the M gamma M high symmetry direction. So this material study actually paper accepted in Nature.com recently. So let's try to understand the crystal structure and the other transport properties of these materials. So here, this is the crystal structure of CuNP4 where it has the hexagonal p63 mmc space group, and the NB, there are two NbSe2 layers, and in between these two NbSe2 layers we intercalated cobalt atoms. So these cobalt atoms located at the 1/4 octahedral location that make the crystal as a centrosymmetric one. So cobalt atoms, they are ferromagnetically aligned in plane, but they are stacked antiferromagnetically along the out of plane direction. So this is one of the required property of exhibiting the ultramagnetic properties for a particular materials. So here, this is the top down view of CuN4 where we can see clearly the intercalated cobalt atom locations. So this is bulk 3D brilliant where we mention the high symmetry direction as well as the different Kz plane. So we will be more interested to study the electronic structure along the gamma m direction at Kz is equal to pi over 2c, which is actually predicted to host the potential ultramagnetic spin speed polarized band along the gamma m direction. So in the resistivity measurement, we can see that resistivity increases with the increasing of temperature. That actually shows the metallic nature of this material. So it also has the king at around Tn is equal to 267 Kelvin, that actually transition temperature of CuNP4 So this king also nicely present in the susceptibility measurement along the c-axis. At the same temperature of 267 Kelvin. So this is the spin resolved electronic structure that actually predicted to host the alternating spin spinning phenomena just below the Fermi level along the gamma m direction, but there is no spin polarization along mk or gamma k direction. So after getting the prediction of these materials, we carried out the RPS measurement to study the electronic properties of these materials. This is the Kz dependent measurement was measured from the photon energy of 40 to 110 eV range, and we clearly resolved the periodic pattern along the Kz direction that allow us to put the high symmetry points. This plot is just 170 MeV below the Fermi level. So all of this electronic structure and the Fermi surface actually started in Kz is equal to 0 plane, which is not our required or desired direction to study. But here I just showed the electronic structure and Fermi surface in the other plane also. So here we can see that the Fermi surface has like a pocket at gamma, and there is one dog bone shaped pocket at m point. So we also carried out the plot of along the m gamma m direction, and we can see that there are like hole like bands and the electron like pockets at gamma k direction. So this is our required plane that actually we wanted to study, which is Kz is equal to pi over 2c, and the corresponding photon energy is 55 eV, and in all of the RPS measurement carried out in temperature 7 Kelvin. So here we can see that different pocket at gamma and m. So at the smaller pocket gamma, it increases in higher binding energy or in the constant energy contours, and C is equal to minus 70 MeV and minus 150 MeV. That actually indicate the hole like nature of this pocket at gamma. So there is dog bone shaped pocket here at m, so which is clearly resolved in the spin resolved DFT calculation. So this dog bone shape pocket is actually has polar spin polarization one is for spin up and another is for spin down. So therefore we take the data at kg is equal to pi over 2c, which is corresponding photon energy is 55 eV, and here it is the zoom view of this Fermi surface where we overlay the DFT calculation, and we see that in the dotted box, inside the dotted box, which is the M point, so we overlay the DFT calculation which is exactly matches with the dog bone pocket here. So this dog bone pocket actually spin polarized band, so that's why we take the cut along gamma M direction here in the figure C, and we see that so there are in the MDC we can see that one is for spin up, another is spin down. There are two peaks. Yeah, we also carried out the Lorentzian fitting of MDC, integrated the 5 mm below up to the Fermi level, and we can see that clearly there are two bands. One is for spin up, another is for spin down, and which is very symmetric along the 0 to positive momentum and 0 to minus 0.8 the negative momentum as well. After that, we carried out spin resolved RPS using Scienta TA30 hemispherical analyzer equipped with 3D spin bleed detector. So here we bring again this spin resolved calculated electronic structure to show the different vertical cuts where we actually take the spin resolved EDC extraction here. So all of the three vertical lines at kx is equal to 0.33, kx is equal to 0.4440, and kx is equal to 0.46 per Armstrong. And we clearly see that this EDC has like spin polarized band. One is for spin up, another is for spin down, which is clearly visible. All of the three EDC extraction in the enlarged view, that one is for spin up and another is for spin down. They are nicely resolved. So in figure D we showed the spin polarization which is taken in the figure B and C as well as. So again we take another cut 2 which is not gamma M, which is actually M to K. So at M we expect there will be spin polarization band. We actually resolved in the spin resolved EDC measurement, but when we move from M to K, then there should not be spin polarization, which we actually studied here in this plot. From gamma M to gamma K direction, here we can clearly see that spin resolved EDC band, and one is for spin up and another is for spin down, but there is no spin polarization at gamma K. Finally, I would like to summarize that CONB4 is a ultramagnetic material which has transition temperature at 168 Kelvin, and we observe the spin polarization band along the gamma M direction at kg is equal to pi over 2c plane, and the corresponding photon energy is 55 eV, and all of the spin polarization we resolved according to the spin polarized DFT calculation, RPS measurement, as well as spin RPS measurement. I would like to thanks to all of my colleagues and beamline scientists at ALS and SSRL, and I would like to thanks to Professor Igor Mazin for the theory support and Professor Nirmal Jigamiri for crystal growth and characterization. Thank you so much to listen to me.